Okay, so the next speaker for this session is Anna Lee. Anna is a graphics and wearables product architect at Meta in the Reality Labs. Previously, she spent 15 plus years at Intel as a product architect across media, graphics, GPU architectures, and AI/ML, contributed to 6 generations of Intel GPUs and products such as HoloLens 1, the first Intel server graphics card, network servers, and thin and light laptops. She holds a Master of Science and a PhD from USC, and a Bachelor of Science and Master of Science in Computer Engineering from Carnegie Mellon. Please welcome Annalie.
Thank you for that intro. So yeah, as Emmanuel said, I am actually a wearables architect at Meta. So I'm not here speaking on behalf of Meta, because if I were, I would be teaching you how to make glasses, not talking about this topic. This is more related to the work that I do with Emmanuel and other folks in the processor database committee, where we talk about larger compute trends, and more based on my overall, 15 years as a computer architect. So what is the AI memory wall? For folks who actually have been tracking this, oh, sorry, I also forgot to introduce my collaborator, Rosa. She is my roommate from grad school. She's a EE and neuroscientist at Hong Kong City University, and she made a couple of these slides that I will point to her when we get to. Yes. Okay. So as I was saying, what is AI memory wall? For people who read tech blogs, there's been a lot of conversations about this. But before we get there, I'm going to just briefly cover some of the topics that other folks have talked about here, which is AI on the verge of AGI? There's obviously a lot of disagreements about this, right? The timelines are very wildly, and a lot of people say what we have today with AI are really narrow, what we consider narrow AI, not general purpose. And obviously, I think some folks have talked about the economics aspect. Is there an AI bubble? How close are we to it? There's arguments for and against it, right? There's the fact that people believe that the valuations are completely outpacing the current value. But then there are other people saying, hey, there's, as we've talked about here, there's real productivity that people are using AI for. I'm not an economist, and I am not an AI researcher. I'm not here to talk about any of that. As Neil pointed out, I'm actually here to talk to you about the fundamental limits of computer architecture and where we're going in the next few years, and what are some of the key trends and limitations for AI scaling. Particularly, I'm going to talk about memory. So how did we even come across this memory problem to begin with? And to be very clear, I'm talking about hardware memory. So this is DRAM, SRAM, how we do actual processing. So as folks are probably aware, both neural nets and LLMs, I don't want to, well, created today's AI memory problem. There is the fact that there is catastrophic forgetting as a part of LLMs, just by definition of how these algorithms work. The fact that they reprocess memory and have catastrophic forgetting. This means we have to constantly retrain data. They're very large context windows that are VRAM hungry. And essentially, this is what we call brute force scaling. This is how those algorithms first began. But as I'll talk about later, this is not the current approach. People are getting better about this. So up until now, there has absolutely been this idea that bigger is better. We've seen this massive parameter explosion between ChatGPT 1 to 4, right? And so this means it gets more expensive to train the data sets. And for people who are not familiar with computer architecture, GPUs and TPUs and any machine learning servers that do this training data is consistently accessing memory. That means they need faster throughput, they need higher capacity, and there are many physical demands on that architecture. So what is this AI memory wall? As I mentioned, vast number of parameters, there are huge training data sets, very complex inputs. The network conditions are very challenging, and you still have to store a lot of context to even make it useful. Now, why did we do this? A lot of people will say, well, why didn't you just build more efficient algorithms? Wouldn't that have been easier to start with? But I think that's not really how computing as a phenomenon had worked. So I know I'm dating myself quite a bit, but my last year in grad school was when Stanford won the DARPA self-driving car. And this was in many ways done with brute force compute. It was the first introduction of using LiDAR live, a lot of server compute. And one of the reasons that they actually talk about the fact that it was using diesel was purely because that's how much power it took to run these servers. Now, people might say, hey, that happened in 2005. Why are we still figuring out how to get self-driving cars on the road? And I think this is like a classic March of Nines, right? This was revolutionary. It got us to the 90%, right? It was able to cross the desert in record time. That had never happened. However, to mature it into an actual car that you would send out to the road with all the conditions they can come across, all of the regulatory and safety checks you have to get across, now you are moving from what was basically passing a 90% case to a 99 or even a 99.9% case. And each time, those leaps took almost a decade. And I think one of the ways that we need to think about this is, where are we in terms of this evolution in AI? I would argue that we're actually still pretty close to the beginning, not the end. So I'm sure most folks here have heard of Moore's Law. Certainly anyone in computing have been living with this since the 1970s. That is almost 50 years. And the basic premise of Moore's Law is that the number of transistors on a chip was going to double every 2 years. There was also an economic perspective to this law, that by being able to shrink the density, that you were also able to scale this in a power-efficient way and in a cost-efficient way. Now, one of the things that we've seen over the years is the number of transistors on a chip is actually still doubling. That is still happening. However, it's coming at a higher and higher cost. Although some of that is supply and demand, and whether or not those economic costs are a factor of the pure technology or economy. Like I said, not an economist, I'm not going to talk about that. What is not up for debate, though, is memory no longer is scaling. This actually happened several years ago. Folks can see that based on the TSMC scaling for SRAM, we basically flattened out already starting at 2022. This is in the past, not the future. So this is something that people in core compute technology have had to contend with already. This is basically caused by capacitor limits. We are already at the size where we can produce capacitors at reliable sizes. By trying to go smaller and trying to increase density on memory sort of in a brute force way, we basically are going to introduce many more manufacturing defects. It's going to lead to increased leakage. So it's actually, the smaller you make it, the less power efficient it actually is. And it creates a bunch of interconnect bottlenecks because memory wiring, the physical wires you connect to these memory chips don't scale proportionally. So these are real physical limits we're coming up against. So what does that all mean, essentially? The way I frame this is, if computer science folks were hoping that the hardware folks are just going to continue to give you guys continuous scaling like we have in the last 50 years, it's going to take a lot longer than you're used to for the cavalry to come and save you. But there are various memory technologies looking at improving these memory bottlenecks. I think folks are probably very familiar with high bandwidth memory. This is actually what's on all the NVIDIA GPUs today. This is one of the core technologies that allow them to scale to higher and more dense compute. There's also things like in-process memory, compute express link, XCL, and 3D stacking. These are things that people are actually already doing in the industry on hardware. Now, it sounds, most folks would look at this and say, this is quite a lot of techniques already. Why are people still in the tech field concerned about this memory wall if there's so many things we could do? These are in many ways, the previous technologies I've talked about are kind of Band-Aids or single-use Band-Aids. They are very costly. Sometimes they don't necessarily improve power efficiency. They take longer to scale. And more importantly, certain technologies like 3D stacking don't continue to scale linearly. You can't move from 3D to 4D. I mean, that's a joke, but basically, most of them have real limitations, and they will take much longer. Another example of this, and this is all public data, about when HBM expects to double in capacity. So HBM is essentially not just high bandwidth, but low latency memory. And because of this, you can see that we are projected by the companies who are currently working on this to double in 4 years. That is much longer than 2. So what's the way out? So I've been transparent with some of the folks at this conference that I've talked to that when I first started making this slide, I was not very optimistic because as Neil pointed out, we're not showing exponential compute growth from the hardware side. But I think people are actually we are seeing this massive resurgence in compute efficiency. I think the fact that Richard Sutton and Andrew Berto won the Turing Award is actually a signal to the industry to say, compute efficiency matters again. We want to move away from brute force compute. Whether or not we can is besides the point. There's a willingness to further look at this. And there is very heavy optimization in AI companies looking at compression and optimization techniques. So why is reinforcement learning more memory efficient? Why is it a signal that people are aware of this problem and actively working on trying to address it? So the way reinforcement learning works is it saves memory and it fine-tunes very small parts of the model. It doesn't just continuously retrain. It also does a lot of pre-training by updating parameters instead of updating them all at once. And it does a lot of fine-tuning of weights, which that all cuts down on memory. Now, folks are probably familiar with real-world example of this, which is what DeepSeek released last year, which really focused on things like MOE, which is sparse activation, and MLA, which reduces memory. Of course, one of the things people might argue is that DeepSeek is not generic. And by definition, a lot of these optimizations you will see will have limitations on how it scales and into all ML and AI applications. This is actually something my collaborator, Rosa, worked on. This is another way of looking at doing machine learning in a much more memory efficient way. And that is looking at smarter networks. So instead of using standard neural nets, we do preferential attachment to both to network generation and continual learning. But she can speak to that if anyone has questions. This is hardly the only algorithms people are looking into. There has been, the last few years, massive growth in this area. Quantization is something that people now apply to ML models across the board. And this is basically just using lower precision numbers for models and weights. This actually has been a trend in neural nets for much longer. And people are just starting to apply them more generically across the board. There's other things like, sparse LLMs, which I touched on, and DNNs. There's also cache optimizations. So you definitely see this general trend of going to smaller models, less memory intensive, and using smaller models to train larger models. This is a general trend you see in the industry. So the question that folks are probably going to want to answer is, can hardware computer architecture scale to meet AI demands? I think I started my topic basically saying no. If we're just waiting for hardware, the answer is no. On the other hand, we are seeing a lot of growth in algorithmic techniques, and those are starting to see real significant gains in actual model deployment. So this is based on, I think the formatting got screwed up a little bit. But as you can see, there are many quotes for this specific slide, but they basically look at memory footprint in terms of inference. So we're actually scaling anywhere from 2 to 4x year over year. So this is annual improvement. There's also model efficiency speedups from 2 to 3x, and in some cases, model compression 3 to 4x. So, and a lot of models today will deploy all of these techniques, and they are seeing factors of sometimes 20 or more in compression. This is actually the last slide. So as I said, the hardware, memory, and I/O limits are not durable. Those are not the only way we can solve AI. These algorithm solutions are very critical for efficiency and scale. Reinforcement learning and other techniques are just good examples of this. But this is clearly a trend that the industry needs to continue. But lastly, I think I want to touch on something that I basically said I wasn't going to talk at the start of my slide, which is, are we going to see more growth in AI? I think in a lot of the presentations we've seen here, we have seen people trying to deploy AI in new and unique ways. And if that happens, then regardless, the hardware demands are going to continue to increase. And therefore, we still have to find a way around general computer architecture to solve the problem. That's actually the last of my slides, so yes.
All right. So if you will forgive me for a second, I'm going to translate for some of the economists in the room for one particular thing, because I think that the idea of a memory wall is not necessarily clear if you don't sort of follow computer architecture. So for the economists in the room, you can think of this as like you have a bunch of machines that are working, that's the processor, and you have the storeroom where you have the inputs to those machines, that's the memory, right? And so like what's happening is we keep getting more and more machines, yes, and we're not getting more storeroom to keep the inputs in, right? And that means it's very, very likely that you start having machines that go idle, right? And or you just can't get much of a benefit from them as they get more. And so you end up with this situation where we're sort of stuck with like, you know, memory not miniaturizing, as you said. And so we're not able to more. How do you, correct my analogy.
Oh, sure. I think that's a very good analogy. I think it's also one of the reasons why you're seeing this massive growth in data centers. It's essentially, if you want to scale your workload, the only way you can do it without changing your algorithm is to put more machines down, right? And that obviously is not cost effective, power effective, and you will run into physical limitations for how large your models will grow because the pure capacity sizes will start to become limits. So
let me ask.
Yes, and you feel free to translate
in the voice of the audience for here. So, yeah. So why can't we just like take our chip and plug it into something off chip that has a huge amount of memory?
Perfect. Yes, I think it all has to do with latency, right? So there are already many memory techniques, like for storage, for DRAM, that actually have bigger capacities and wider pipes. But the problem is the latency to access that memory grows as those capacities grow. So basically, the same workload will just now take longer to run. And then a lot of the scaling that people talked about, I can complete this task in 5 minutes, that will just continue to lengthen, even when you're using AI, essentially, yes.
And you mentioned that capacitors, which are the sort of heart of memory,
yes.
sort of have hit this limit. So
yes.
why is it that for most of the history of Moore's law, as we shrunk them,
yes.
they kept doing what they wanted to do, and now, which we wanted them to do, and now all of a sudden, like, they're not able to do it?
I think it's really that we are starting to get to the limits of physics of both the transistor and the capacitor technologies. There are folks here who asked me when I talked about my topic of, well, why are we not just considering quantum computing? Like other ways, like other fundamental ways of doing computing that would bypass some of these problems. And the truth is that would lead to almost a fundamental infrastructure change. One of the core aspects of computing in the last 50 years is by doing this raw transistor growth, what you were able to do is reuse the basic same computer architecture. We defined what a CPU and GPU was in the 1960s, right? Even though they have changed significantly, the fundamental architectures haven't changed. And same for essentially the software stacks that ran on top. Even though language evolution has changed significantly, how they process that compute hasn't. Whereas if we move to something like quantum, that is almost completely reinventing the entire stack. And that is a massive, not only a massive investment, but also will take many years to mature. And some of these memory problems, as I highlighted, we hit in 2022. These are not problems that are happening far into the future where those techniques can come and save the day. You know, they're gonna take 10, 20 years to mature if we even start investing in them now. And many people are, by the way, investing in some of these more exploratory architectures like quantum. That is absolutely happening. But that is just not going to come fast enough to solve some of these problems.
And then my last question, then I'll turn it to the room. But you know, you sort of started by saying, are we going to get a lot of hardware progress? And you were pretty pessimistic about that, right? Because of memory. You talked about algorithms as still having a fair bit of space to improve.
Yeah. Yes.
How much of the algorithmic improvement do you think is going to require hardware architects to co-design things with them? And how much of this can sort of just happen separately in, you know, the Googles or OpenAIs of the world?
That's a really great question. I think it's an interesting question because actually since the 1990s, all hardware is considered software and hardware co-designed. So all computer architecture actually starts assuming a better software model that will launch in a few years, and then we actually design computer architecture based on where we think that model is moving. So that trend will continue, but I think if you're saying, is there something core in computer architecture that we should be doing along with the algorithm developers? Yes, because you can't actually build hardware that doesn't understand how the software is going to use it. And that, I think, will continue to be a trend. Yeah.
Right. Okay, let's turn to the room.
Hi, thank you for the talk. I had kind of a similar question about like algorithmic improvements.
Yes.
You mentioned in your slide on the DARPA challenge about like diminishing returns to
Yes.
algorithmic improvements at like 90% to like 99.9%.
Yes.
But then you also mentioned later some of the memory efficiency improvements that have been going on, and I'm curious whether you think these are more in the like, you know, pre 90% of improvements or more on the like 99.99%.
I can give you my personal opinion. I don't know if that like reflects what's actually happening, you know, out in the field. But I do think, in many ways, I think the introduction of LLMs, in my mind, is where we got to the 90%. If folks think about pre-LLMs, how, you know, language models worked, how query models responded to prompts, right, it was a complete fundamental shift. I do think right now a lot of these model optimizations is trying to move from that 90% to the 99%. So no longer just a cute research project, very much in the field trying to improve. The question though is this going to be widely and commercially deployable? Kind of, is that between 99% or 99.1? I think that's actually a lot of the questions folks in this audience have been trying to answer. When can we actually replace people in labor wholesale with AI, right? That is very similar to replacing drivers on the road. So a lot of parallels there, but probably not concrete answers yet that anyone can give you. Yes.
This is a really incredible talk, and I learned a lot about what a memory wall represents. So, as one of the economists in the room, thinking about who the actors are, I'm wondering who might be responsible for this innovation if it happens. Is this happening at the NVIDIA AMD level, or is this TM at
yes,
Taiwan Semiconductor, or are Google, Apple, Microsoft going to start making their own chips?
The question you were saying is essentially how much is hardware responsible for, how much is software responsible for? So I think, as Neil astutely mentioned, this is very much a hardware co-design problem, right? So some of the fundamental memory technologies that's happening in places like Micron, NVIDIA, et cetera, they're developing their own interconnects, they are figuring out how to do chip stacking, but this very much has to work alongside of people developing the algorithms like Google and et cetera, and ChatGPT, because for example, I'm just going to take 3D stacking. 3D stacking is putting a memory chip right on top of a processor chip. And the reason they're doing this is to lower latency so that compute can happen faster. But one of the consequences of that is thermals now increase. So now you might have to spread your workload on the software end in a way that it doesn't hold as much heat capacity, meaning tasks have to be processed faster and they have to be less resident in how long they take to compute. So I would say both, but certainly there's ones hardware is more responsible for and other ones that software have more impact or influence in. Yeah.
And just sharing something that you had shared with me last night at dinner, right? When we were talking about thermals, what we're talking about here is that the limits of running these chips fast is dissipating the heat, because when you do the processing, and you can imagine if you you get rid of a lot of your heat off the top, and if you put a whole bunch of things on top of it, for memory for stacking it, now it's really hard to get that away.
Yes.
And so it's your thought is that, what you told me last night is that as you do this, right, you very quickly get diminishing returns because it's so hard to get the heat away.
Yes.
You have to run your chip a lot slower
Yes.
to make sure that it doesn't overheat.
Right. So when I was at Intel, one of the key things we do with server deployment is actually working on active cooling solutions. In some cases, this is everything, including fans, to literally piping water around the servers to get the heat out. That is actually one of the key limitations to scaling compute as well. So that's where the thermal aspect comes from. So, yeah.
Hi. Very great talk. Quick question. So is there any rough estimation about when we're touching that AI memory wall? Or maybe there's another terminology called the scaling saturation point, meaning that just how roughly the parameter size about the model and the data size is no longer growing given today's hardware limitation? And how many years do we potentially still have to get it?
Actually, I think in some of the charts, like the one I had for how much parameter sizes are growing, and very similar to the diagram that Neil had generated with his graph, is actually if we have not been getting algorithmic scaling, we would have already hit it. That's the truth. That would have already happened. It's only because both of these things are moving together that people are doing software and hardware optimization at once that we have not hit the wall yet. If you just literally took ChatGPT 1, 2, 3 and scaled to ChatGPT 5 pure through brute force parameter size growth, we would have already hit the wall. So.
Yeah, thanks so much for the interesting talk. I wonder, if we see limitations on the hardware, and we know refocus more on the algorithmic improvements and efficiency.
Yeah.
I wonder as well whether like we as well see some kind of limitations there, and like how far we are on like maybe like algorithmics limitations.
That's a great question. I think maybe I'm optimistic. You know, I did my PhD in big data analytics back in 2000, back in 2005. I think, honestly, a lot of the improvements we've seen in software algorithm, no one expected to see. If you asked me back then where we would be now, I would not have predicted this. So I'm optimistic, but I think that might be a limitation of both AI and human ingenuity. And it's very hard to figure out what the cap on that would be. So.
Hi, I'm hoping you can help me understand exactly where this wall is hitting, because there's the picture of the improvements. There's a 45 times growth in hardware, and then there's a big one in the build outs, and then there's the algorithms one we're talking. But my understanding, if it's right, is that Moore's law was only like a 2 to 4x out of that 45x in the hardware.
Yes.
And so losing that's not a big deal. But what I think I'm hearing is that this memory bottleneck doesn't hit in the hardware growth, but it hits in the parallelization, so it comes out of that big chunk. Is that right?
I think yes, or at least certainly in the way that people think about algorithms today, right? So I think it's the way I frame it is, even though that hardware growth has only been 45x, that has actually led to tremendous growth on top of it, right? So I think a lot of times people don't quite understand that just by improving processor speed by 2x, like year over 2 years, that actually unlocked a lot of compute to allow algorithm complexity to grow. So I think even though in Neil's chart, the hardware growth is not responsible for majority of the growth, I do think it's actually a limiter that will squash a lot of potential algorithm development that could have happened, because essentially you hit caps earlier than you expected.
Yeah, so you're saying it hits in the algorithms bit.
Yep.
What about in the parallelization, like the ability to have a huge data center?
Yeah, that too, yes. Because I think, like I said, some of this is going to hit physical limits in terms of how much heat dissipation you can have, how large your data centers can grow. We are already hitting some of those, right? So yes, to your point, there's the, hey, we're just gonna keep throwing more and more servers at it. That will also start to become a limiter, yes. Not to mention how to power it and some of the other things I think other folks are going to talk about.
Okay,
so
last question.
Thank you for this very informative talk. So I know you mentioned there's a lot of what's going on with other computing methods like quantum, which I know is very much in vogue right now. I'm very, very curious to hear your thoughts on what potential impacts of advancements in photonic computing might be, because it doesn't have maybe some of those limitations, even though it has other limitations on the memory wall.
No, those are all great questions. I think, to be honest, I think a lot of the new exploratory computer architecture, their limitations, as I said, are not even necessarily what it would take to mature that technology in itself, but how would the rest of the compute industry have to respond once we move to a fundamentally different type of computing. I think that's actually going to be a bigger limiter. So it's very much a technology maturity limitation than a growth necessarily than each individual one is better or worse, right?
Anna, thank you very much.
No, thank you.